Alright, so today I'm going to be going over question 34, which says the drawing shows a thin uniform rod which has a length of 0.45 meters and a mass of 0.094 kilograms. This rod lies in the plane of the paper and is attached to the floor by a hinge at point P. A uniform magnetic field of 0.36 T is directed perpendicularly to the plane of the paper. There is a current I, which equals 4.1 amps in the rod, which does not rotate clockwise or counterclockwise. Find the angle theta. And the hint is the magnetic force may be taken to act at the center of gravity of the rod. So I'm just going to walk you guys through the solution right now. So here, first of all, here I have just the diagram drawn out. So the rod is 4.5 meters, or 0.45 meters there, and 0.094 kilograms. So this is what it's going to look like, our situation. Then we have an FED here, which shows all the forces acting on the rod. So we have the magnetic force going perpendicular to the rod, and the force of gravity going downwards, but there's also a perpendicular component of gravity for the rod. And the way you can find out, the way I found out that the force of the magnet is going perpendicular to the rod is because by using, as my physics teacher calls it, slappy. So we have the magnetic field going into the page, and then the current going this way, so the force has to be going out of my hand, so just this way. Perfect. So that's how I got that. And let's see if we can zoom in there. Perfect. Now, so the question says that the rod is not rotating, so we know that it is at an equilibrium of torque. So we have the counterclockwise torque is equal to the clockwise torque, which means the rod won't move. So in this case, the two torques are the torque from the magnet. So I'm going to say T mag is going to equal the T from the gravity, the torque from the gravity, so T grav. So yeah, we want to find, for the gravity, we want to find the perpendicular component of the force of gravity. So we use mg cos theta up here. And for the force of the magnet, we use ILB, so current times length times the force of the magnetic field, which is equal to the force of gravity times, or like the force of gravity at the point of the center of gravity, which is the very middle of the rod, times cos and times theta. So what we're looking for here is theta, but we can do some quick cancellations first. So we have length divided by 2 on both sides, so we can cross those out quickly, and then we can go and isolate theta. So we can go theta equals the inverse of cos times, we have current times length times the force of the magnetic field on the top divided by the force of gravity. And this should give us, this is our final equation, this should give us theta, which is what we're looking for in this equation. So I'll just go ahead and write this out really quickly one more time. So now our current, the value for current we have is 4.1 amps. And the value for the length of the rod is 0.45 meters. The force of the magnetic field is 0.36 Teslas, and then on the bottom we have force of gravity. So first we have the mass of the rod, which is 0.094 kilograms, times the gravity, so the acceleration due to gravity, which is 9.81 meters per second squared. And this should give us our value for theta. So let's go ahead and plug this into my calculator really quickly. So here we go. We got inverse of cos. On the top of the fraction we have 4.1 times 0.45 times 0.36 divided by 0.094 times 9.81 meters per second squared, and this should give us our answer, which is 43.92, which we're going to round up to 44 degrees because we've only been given two significant figures throughout the entire equation. So theta equals 44 degrees. So just a little quick recap. We have to, because the rod is not moving, we assume that the torques are equal. Well, we know that torques are equal because there's no movement, no rotation. So the two torques acting on it are the torque from the magnet and the torque from the gravity, the force of gravity. So we have here FD sine theta, and then sine theta, because the angle between the force of the magnet and the rod is perpendicular, is 90 degrees. Sine theta becomes 1, so we can just, so I just left it out there. And so this is where the torque is acting, which is at the halfway point of the rod, which is the center of gravity. And then the torque from the gravity, we have the force of gravity, so m times g, mass times gravity, at the half point, so length times 2, so that, and then times cos theta, because we want the perpendicular value for mg. And then once we isolate theta, the equation becomes negative, like the inverse of cos, times this fraction here, which is current times length times force of the magnet divided by the force of gravity. So then once we plug in all our numbers, we get 44, which is our answer. Thank you very much.